Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH of a buffer solution containing a base and a salt containing the conjugate acid of that base after a strong acid has been added. For this particular problem, you're asked to find the pH of a 0.300 liter buffer solution that is 0.25 molar ethylamine and 0.20 molar ethyl ammonium chloride after 0.010 moles of hydrochloric acid have been added. So hydrochloric acid is a strong acid. And when a strong acid is added to a weak base solution, and our weak base in this case is ethylamine, then a neutralization reaction occurs. In this case, the weak base is neutralized by the hydronium ion that comes from the addition of hydrochloric acid. So when hydrochloric acid is added to solution, it dissociates into a proton and the chloride anion, but the proton doesn't hang around for long because it's very reactive and it quickly combines with water to give you a hydronium ion. So the neutralization occurs between this hydronium ion and our weak base, which is ethylamine. So that neutralization reaction looks like this. You have your hydronium ion plus the weak base, ethylamine, going to the conjugate acid of that weak base, which is ethyl ammonium ion, plus water. So that water molecule is left over after the hydronium ion has transferred a proton to the weak base, which is a proton acceptor. So notice that this arrow is a one-way arrow going from left to right as opposed to the two-way arrows that you've been seeing in most of equilibrium chemistry. And this is because for neutralization reactions involving strong acids, such as hydrochloric acids, the reactions essentially go to 100% completion, meaning there's not a lot of reactant left over, but there's a lot of product. So we show this as a one-way reaction. So you can use this neutralization reaction to head a table, and it's not an ice table, but it's a certain type of table that can help you ultimately find the pH of your buffer solution, which is what you're being asked to do here. So in this table, we have one row designated as before, so these are the moles of each of the species present before the neutralization reaction occurs. We have the change in moles of each of the species present due to the neutralization reaction, and then we have the moles for each of the species present after the neutralization reaction is completed. So filling out the first row first, we want to know the number of moles of hydronium ion present before the neutralization reaction occurs, and we're given this in the problem because we're given that 0.010 moles of hydrochloric acid are added, and because we have a 1-to-1 molar ratio between hydrochloric acid and the hydronium ion, then if we have 0.010 moles of HCl, we also have 0.010 moles of hydronium ion. So we can put this under the hydronium ion for the column describing how many moles are present before the neutralization reaction has occurred. Next, we want to find the moles of the weak base, which is ethylamine, before the neutralization reaction has occurred. So we're given that the solution is 0.300 liters, so we're given this in the problem. And we know that the concentration of ethylamine is 0.25 molar. We're also given this as part of the problem. So that means we have 0.25 moles of ethylamine per liter of solution. So liters will cancel out, and you're left with 0.075 moles of ethylamine. So we can put this value for moles into our table in the before row. We also want to find the moles of the conjugate acid of ethylamine, that ethyl ammonium cation, that are present before neutralization. So we can do the same kind of thing. You take the known volume that you start with, 0.300 liters, you multiply it by the molarity of ethyl ammonium chloride, which is given to be 0.20 molar. And when ethyl ammonium chloride is in solution, it dissociates into the ethyl ammonium cation, which is what we're interested in here, and a chloride anion. So there's a 1-to-1 molar ratio between ethyl ammonium chloride and that ethyl ammonium cation. So that means if we have 0.20 molar ethyl ammonium chloride, we also have 0.20 molar ethyl ammonium cation. So we can write that 0.20 moles of ethyl ammonium cation per liter. If you do the math, you end up with 0.060 moles. You can put this number in the before row of your table. So there's your first row. So all you need to do here is subtract from each of the reactants the 0.010. And this is because for every mole of hydronium ion that reacts, you'll lose 1 mole of that, but you'll also lose 1 mole of ethylamine. So you're subtracting from the reactant side, but you're going to gain 1 mole of product. And in this specific case, because of this 1-to-1-to-1 molar ratio between the three, you'll gain specifically 0.010 moles of ethyl ammonium cation. So all you have to do is the simple math here, and what you'll find is you get 0.065 and 0.070 for the number of moles of each of the species present after the neutralization reaction is complete. So remember that we're trying to find pH, and to do this we can first find the hydroxide ion concentration using the Kb value for ethylamine, and also the concentrations of ethylamine and the ethyl ammonium cation after the neutralization reaction. So we can use these values for moles that we just found for those two species and divide it by the total volume of the buffer solution, which we're given as 0.300 liters, to find the concentration of both of those species. So in order to do this, we have to assume that the solution volume remains the same after the addition of hydrochloric acid. So assuming we still have 0.300 liters after HCl has been added for the neutralization. So the concentration of ethylamine is going to be equal to 0.065 moles. So this is the value we just determined to be the moles of ethylamine after the neutralization reaction is complete, and you're dividing by that by the known volume of 0.300 liters. You do the math and you get a concentration of 0.2167 molar for ethylamine. You can also find the concentration of the ethyl ammonium cation in a similar way. So after the neutralization, you have 0.070 moles of ethyl ammonium cation remaining, and you divide that by the total volume, which is 0.300 liters, and do the math to get 0.2333 molar as your concentration of ethyl ammonium cation. So the next thing you need to do is to realize what the principal proton transfer reaction in solution is after the neutralization reaction has been completed. So the principal proton transfer reaction in this case will be the base ethylamine accepting a proton from water to give you the conjugate acid of that weak base, which is the ethylammonium cation, plus the hydroxide anion, which is what's left over after water has given up its proton to the weak base ethylamine. The equilibrium equation that describes this equilibrium is the concentration of the ethylammonium cation multiplied by the concentration of the hydroxide cation divided by the concentration of ethylamine. So we know the concentration of ethylamine, we know the concentration of the ethylammonium cation. We can look up Kb in a table of base dissociation constants. So what we want to do is solve for the hydroxide ion concentration, because once we've solved for that, we can find the hydronium ion concentration, and then we can find pH. So rearranging this equation to solve for the hydroxide ion concentration will give you the hydroxide ion concentration times Kb times the concentration of ethylamine divided by the concentration of the ethylammonium cation. Substituting in the numbers that we know that Kb is 6.4 times 10 to the negative 4. Again, this is something you'd look up in a table of base dissociation constants, and we're using the Kb value for 25 degrees Celsius, so we're assuming all of this is occurring at 25 degrees Celsius. You know that the ethylamine concentration is 0.2167, so you've just solved for this concentration after neutralization has occurred, and the concentration of the ethylammonium cation after neutralization has occurred is 0.2333, so you've also solved for this concentration. So you do the math to find the hydroxide ion concentration is 5.9429 times 10 to the negative 4. So next you want to find the hydronium ion concentration, and you know the relationship that Kw is equal to the concentration of hydroxide ion times the concentration of hydronium ion. If you rearrange this equation, you get the concentration of hydronium ion is equal to Kw divided by the concentration of the hydroxide ion. And if you take the Kw value of 1.0 times 10 to the negative 14th and divide into that the value for the hydronium ion concentration that you just solved for, which is 5.9429 times 10 to the negative 4, what you get is 1.6827 times 10 to the negative 11. The last thing you have to do to find pH here is say that the pH is equal to the negative log of the hydronium ion concentration. You've just solved for the hydronium ion concentration right here. So if you substitute this number into this equation, you'll find that the pH is equal to 10.8. So here's your solution. You ultimately wanted to solve for the pH, and you've done that, so you're finished.